Dear participants, good afternoon. This is Lakshmi Prasad. I'm going to read our profile of, I'm going to read the profile of our resource person, Dr. B.V. Reddy Garu. Dr. B.V. Reddy is a professor in Department of Mechanical and Manufacturing Engineering, Faculty of Engineering and Applied Science, Ontario Tech University, Oshawa, Ontario, Canada. Prior to this, Dr. Reddy also worked as an associate professor in Mechanical Engineering Department, University of New Brunswick, Fredericton, Canada. Dr. Reddy received his MTech and PhD degrees in Mechanical Engineering from IIT Kharagpur, India, under Professor P.K. Nag. Dr. Reddy led funded research projects in the area of fluidized bed combustion, biomass, biofuels, and energy systems. Dr. Reddy has published 210 papers in referred journals and referred conference proceedings. He also involved in the organization of international conference as conference chair, track chair, organizing committee member, advisory committee member, etc. Dr. Reddy has delivered keynote and invited presentations in many international conferences. Dr. Reddy has also received Best Professor Award for teaching excellence both in India, VIT Vellore, as well as in Canada. Thank you, sir.
Yeah. Okay. So thank you very much, Prasad Garu, for the nice introduction. Okay. So before I begin, let me thank Professor P.V. Kumar, the coordinator, for giving this opportunity, and also the amount of effort Professor Kumar put through even my friend who is Dr. Bala Prasad, who is a professor in a college, RVR and JKC in Guntur. Anyway, it's good. Okay. So what I will do, as you might have got it. First of all, I should tell you, I tried my best to be there by 3:30 p.m. because right now here in the morning in Canada, the time is 5:10. So a few minutes, don't worry. I will take few minutes if needed, the continuation. So the two topics, two lectures, if you have seen the title, the first lecture which I will be speaking now, it is going to be on the sustainable development, role of second law of thermodynamics. Why I choose this is as you have seen the title of this ATAL FDP. It is on sustainable development. It focuses on hydrogen energy technologies and their advances or developments. And you might have had speakers, many speakers focusing maybe more on hydrogen. But this sustainable development. Are you able to hear me?
Yes, sir.
Okay. This sustainable development is such a growing or important topic worldwide. Is it okay? My volume, everything, please.
Yes, sir.
Yes, sir.
Okay. So I will be, as I said, first I will give you some advances, developments, importance related to sustainable development, and particularly focusing with reference to second law of thermodynamics. We all know laws of thermodynamics, and these days, I don't say these days, at least I tell you, from late 80s or 90s, second law is receiving a lot of attention. Okay. So the way I structured both these lectures are, it's not just talking about few equations or something which is not the exact benefit of when you have expert lectures like this. So to give you some areas where maybe you are a professor or you are a PhD or you are going to be a graduate student in future in case, so they should help you some way a little bit for your growth, as the program itself indicates, which is FDP. Okay. So with this, we get on. So what I will do is I'll give you a little idea about the growth, the demand for energy worldwide, and what are the reasons, like particularly, as we know, the population of the globe is growing. And not only that, there are many countries which are developing at a very faster rate. So that means they need more energy for their development, which I'll show you in a little bit. There are consequences depending on what sort of energy sources we are using, you know. So that is something is gaining a lot of attention in terms of pollutants, greenhouse gas emissions, particularly which are responsible for global warming, climate change. Then what is the role of laws of thermodynamics, particularly second law? I'll show you how it is contributing towards a better side of designs development, ultimately leading to sustainable development. Okay, so now this one here, if you notice it, please, these numbers, even if you people go these days onto Google, you will find it. The whole idea behind is, if this is like in 2000, if you see typical energy mix, you can see different colors indicate different energy sources. But what is the thing that commonly you notice is, particularly the coal, oil, and natural gas. These are the ones they carried a lot. And a lot of oil may be going towards transportation, but other two are lot goes in energy sector and also industrial sector. So that means put together they contribute. They also cause issues, particularly with emissions and CO2. And look here. So if you look at other side of the, the same figure, these are projected figures. So though there's a lot of interest, lot of effort by governments across the globe to increase renewables, no doubt. You see that there is a tremendous development, tremendous attention, and renewable share is increasing. But at the same time, as I was saying, many countries are trying to develop, they want resources. So they are utilizing energy resources in a bigger way. So that means the share of whatever you are seeing here, these colors, which is the coal, oil, and natural gas, they are still continue to increase a lot. It is not just about percentage, please. If you notice in terms of totals, when you multiply with the same percentage, actually their number is much more. And if you see the oil share is a lot for transportation because vehicles are coming on a bigger way on the roads. So put together, what it tells you is two things. Number one, we need to increase renewables, that goes on, but there is no overnight magic where these three can be replaced. That means there is a lot need to develop better or advanced or efficient technologies so that emissions can be reduced, so that we address whatever the climate change or leading global warming and sustainable way of living. Okay, so now if you are wondering, okay, so I'm not here, because a lot of times when we teach or when you read in the thermodynamics, you see laws, and we see first law and second law. So we know first law of thermodynamics, which is law of conservation of energy, which talks about energy balances. It only talks about energy balances. It doesn't indicate or it doesn't bring out anything related to the quality and direction of any energy process or source. Okay, so now if we go to the second law of thermodynamics, that's what it's going to tell you. Typically those two, that is the quality and the direction. So that's where we come across what you call the entropy, which is a very classic one, and entropy generation. And as I said, so from at least last 15-20 years, the term exergy used a lot. I tell you in this lecture, when I go to the second part of this lecture, I will show you the details related to exergy and exergy analysis, why it is gaining importance and what their consequences are in general in engineering systems design, overall on environment and sustainability. Okay, so now please just observe as I put you some of the material. The way I have assembled is in a way you can clearly see on one side the first law nature, also the second law. So this is a typical steam power plant, which was taken from Moran Shapiro, a classic book. Even Professor Pikenar book has, very big details. So the idea here is, as I said to you already, my focus is to show you the developments, to show you the role of second law in sustainable development side, and also show you opportunities where there are a lot of research areas we as a faculty or you as a faculty graduate student, depending on what role you are, you can explore to work on. Okay, so in this typically steam power plant, which you have an idea, as I said, I mean, this is what the technology that is utilized even today in a bigger way, starting from 1882 when the first power plant was built to generate power. So we have here a boiler, turbine, condenser, and a pump system. This all and coupled with the electric generator. So the whole idea is this operates on a modified Rankine heat cycle, and then a lot of work is going on. So as I said, I'm not trying to teach you the analysis or the details here, which most of us know it. Now the question is, even today, if you notice it, people do research. Even there are a lot of research papers, people are conducting still research, whether it is on the cycle, efficiencies, parameters, multiple heaters, reheaters, all those things. So that means there's a lot of research that is still going on this performance side, whether about the cycle modifications, whether about looking into the parameters with the steam, pressure, temperature, all those, the blade materials, blade advances, all those things. So the whole idea behind is how to improve the performance, including co-firing. I don't know if people have heard, there are a lot of research that goes on in this boiler, because there are advanced boilers which are called fluidized bed combustor based, where it is not, most of the fuel is used is coal. We can have biomass, and a lot of biomasses can be co-fired with the coal, and that way emissions can be reduced. So the whole idea is all these along with the co-firing is to reduce emissions. Now the question is, what is the role of second one? As we see now, I mean, maybe I'll put these advantages next. First, I will take you to a typical combined cycle power generation. Again, when in a course like power plant engineering, we teach this. So if you notice here, please pay attention. So this is what is called a gas cycle or the topping cycle. So this is the compressor where air is compressed to designed conditions, the pressure, then it goes to a combustion chamber. So most of these, the way it is, are the way you see on this diagram, this shows you either a gaseous fuel or a liquid fuel. So mostly not oils. It is typically either natural gas or some other form of gas that is used in this combustion chamber, which I'll explain as I go through. Now, these combustion conditions are controlled. That means air fuel ratio in a way to match to this gas turbine. So this is where you see a generator is coupled with the gas turbine. So the whole idea is we burn the fuel, produce high pressure, high temperature products which expand in the gas turbine, which drives the generator. Now the question or the thing that you should notice here is, till 80s probably these gas turbines, their blade materials, their range of operating temperature was very low. And later on, there was so much advances, that today we have gas turbines where they are, the inlet conditions are as high as 1350 to 1375 degrees centigrade. So the meaning is, this has a gas cycle, which, it operates on the Breton cycle, will drive the generator producing power. So now the question is, if you observe, as I said, when we have a high gas turbine, a gas turbine that can operate with higher inlet conditions, temperature. So for a given pressure ratio across this turbine, so when you see the gases, waste gases that are coming out from the turbine, their temperature is very high. So that means, using them just to heat the compressed air, or that is not the option from first law point of view. So these gases are now taken to a unit called HRSG. If you are able to notice here, this is called heat recovery steam generator, which is basically a heat exchanger. So the whole idea is part of the waste heat from these gases are recovered and steam is produced, typically superheated steam. So now this superheated steam is taken to a steam turbine where it expands, producing mechanical work that drives this another generator coupled to it. So that means we are producing electric power here. Then you have the traditional steam cycle components, including condenser, pump, all those feed water heaters, whatever the combination, cooling towers, etc. So if you notice this, the way this cycle, the way this whole system is arranged is, I mean, these are combined heat engines. So I'm not able to draw here quickly. Had it been in the classroom side by side, it would have been used the board to explain. So what you see is if you have a heat engine one, this is, we are giving heat input, we are producing work output. The waste heat from engine one is utilized to, again, produce some working fluid and drive engine two, which produces work output. Again, there is a heat rejection. So basically, these are two combined heat engines. So if you represent efficiency, thermal efficiency of the first one as eta 1 in case, and the second one as eta 2, with a simple combined heat engine relations, if you look in any power plant book, you can see it. The combined efficiency of this system, the way you are seeing on the screen, is the combined cycle efficiency is eta 1 plus eta 2 minus of eta 1 times eta 2. In a simple way, imagine if you are, going to take them, even if each of them are going to operate with a thermal efficiency of 0.3 and 0.3, their combined thermal efficiency is 0.3 plus 0.3 minus of that product, which is 0.09, is equal to 0.51, which is 51% thermal efficiency. So the meaning is the efficiency goes much, much higher. And as for second law approach, we are trying to utilize the waste heat, trying to produce some work, and overall reducing the waste or the heat losses and leading to its improvement. So the approach of second law is leading to a better system design, which improves for power output, efficiency, reducing emissions. Then the question is, as I said to you here, it's a gaseous or liquid fuel. And as I said, no oils are used. Even in Gulf countries, they don't want to use oil. Rather, they use only gas because oil goes, most of it is supplied to transportation sector. So then, if this is the most efficient way, today in the globe, the power plants that are the most advanced, which produce power with higher efficiency, are of this technology place. You can see there are plenty of them across the globe in almost many countries. Now, the question is, what about emissions? We are talking not only second law, we are talking sustainability side by side. So I said, there is a way, a lot of research goes. People are doing even in a big way, even today. So as efficiency improves, for the same fuel input here, when we get more work output, means CO2 emissions per kilowatt or megawatt, whatever way you put it, it goes down. Now, how to reduce even it further? So I think, this is where I wanted to show you. See why these are getting so popular. So that means their efficiency overall is very high. And depending on what sort of system you're talking, if it's a natural gas based, typically it takes much less time to design and construct them, and low emissions. And overall, when the efficiency is high, it leads to better economy. Okay. So no, even if you have any questions in between, I'll give time. But first, I want to explain a few materials before I give the room for any interaction, please. Okay. So now, what is the benefit if you, as a FDP attendee, that I benefit? So as I said, there are many areas further that needs to be explored. So that means, how can these emissions be further reduced from this type of plants? That means, is there a room to have natural gas with biomass still operating in the combined cycle mode, that in co-firing? Yes. And a lot of other types of biomass, parameters, and the role of all those, including emissions, emission reductions, economics. I will show you some, sample research and the role of different parameters, how do they influence. Okay. So as far as the analysis is concerned, as I said, if you use the basic first law, second law way, we can approach to get all the equations, then create a code, and then it can be run. So I'll show you now. This is one of the postdoctoral fellow who worked with another professor, Mark Rosen, and me. And I'll just show you, I'll explain, as I said, the role of it. See, if you notice this diagram, don't worry. Whenever you see a power plant configuration, we see a lot of components, because they do have a lot of components, the whole system, the way it is integrated. So here what you are seeing is basically, this is a compressor system, please, of the same combined cycle with intercooling arrangement. Now what you are seeing here is, these are gas turbine systems. divided into high pressure and the low pressure side. And this is where you see the combustion chambers. Okay, so the main combustion chamber and the reheat combustion chamber. So this is where you see the fuel. Assume that we are using natural gas. This is based on natural gas system. The way you see is here, you have the topping cycle with the generator, the way I showed you in the earlier diagram. But what you are going to see is two things, two modifications. Notice it. This is where you have a lot of room to research, to do a lot of research, please, afterwards. Okay. So I will email 3 selected papers. I already told the coordinator, Professor Kumar. So this is one of the paper I will email so that all of you will get it. So if you notice here, not only natural gas is the main fuel. So if you see the compressed air, please, this compressed air is going into a supplementary firing chamber. Here, biomass is going to be fired. As you know, biomass, which is typically a carbon neutral. We have a lot of biomass available. So how it is fired, we have different options. Even if it is only in combustion mode here, if you take like the way it is shown. So the compressed air, as it goes inside the tubes, typically in a heat exchanger, it is being heated to a designed value. So if this is state 4, this is state 5, we are designating state 5. Let us say it is 100 degrees more than state 4 value. That means that much heat is recovered or extracted from burning biomass. So what happens is, for these turbine selection, whether it is a GE, whatever the turbine category it is, what conditions they are, for the same input conditions, now we are going to need less natural gas firing in these combustion chambers. So meaning is, for the same, this is the generator arrangement, whatever the configuration that we set here, now we are trying to fire less natural gas because we are able to extract some heat from this supplementary firing chamber. So the overall idea is less natural gas, so we have less emissions. Then again, here the story is same. So after the gases expand in the gas turbine system, producing power through this generator, this waste heat, which is basically nothing but, if you recollect, when these gas turbine chambers operate, please, basically, though we supply compressed air, we burn here through natural gas for the system that is shown here. Basically, the air fuel ratios are that means air ratio is so much, there's a lot of oxygen available, plenty of oxygen. So that means we can burn biomass here. What type of biomass that is chosen? There are many types, but once it is, so now what we are doing is, the way it is, this arrangement is, there is a steam cycle at the bottom. So steam is produced using the waste heat from here. And then the steam cycle is operated with all those components the way shown and with the generator. So basically, this is the same combined cycle that I showed you in the earlier figure with 2 modifications. One, we are bringing a supplementary biomass-fired combustor where we are able to extract some heat for the compressed air, and then we are using that along with this waste heat, the biomass energy for the bottom cycle. So the whole way is this is brought back into a co-fired mode, and depending on the type of biomass, amount of biomass heat input for the same power plant rated output. Not only, we are using the biomass which is classified as a renewable side, we are reducing emissions a lot. So this is where there's a lot of work that needs to be done, people are doing, and in future, a lot of these power plants will be modified with this type to bring down the emissions, meaning is leading to sustainable development. Again, as the second law point of view, it's a combined cycle mode efficiency is very high. Now let us say, I'll just show you, when people, as you know, a lot of you may be already professors, when you publish paper, you know how much effort it goes to do work and then to publish. So people spend months, same story. This PDF has spent a lot of time in generating a lot of the things. I'm trying to show you here in few minutes, So as I said, when you go through the details, you can see it. If you have any doubt, you can come back to me. My email will be there with Professor Kumar. So here, typically, please observe, just a simple case is shown here. We have natural gas, which is typically methane. Then there are different types of biomasses that are chosen in the study. So whether you take wheat straw, wood chips, or some other wood or varieties, they vary from location to location of the globe. So that means we need to account their composition depending on where you are analyzing. So the whole story is all the details were considered and investigated, and it has been found a good chunk of CO2 goes down for the same power rated of the combined cycle. So as you can see, I think it comes in the next slide, I think. Oh, sorry, it did. The results were not put here, but they are available in this paper, which I'll email. But what I am saying is there's a good amount of CO2 reduction when biomass, as I said, was co-fired with this combined cycle. So this is how a combined cycle is transformed into a co-firing mode, not only to utilize the second law for better efficiency approach, but to reduce emissions by co-firing biomass. Okay. So then what other ways? As I said, ultimately today, whatever we talk, everything in the energy in general, in the engineering side, we focus on sustainability. The word you hear a lot, it doesn't matter which engineering it is, sustainability word is a very common word, and sustainable development. Okay, so then what other forms? So now there is there a way to utilize solar energy? I'll show you. And is there a way to utilize others with to reduce emissions? And a lot of times, as you can see, natural gas plus solar, the hybrid mode, which I'm going to show you, there is a lot research, roll-off system, configuration, operating conditions, etc., that can be investigated. For the same, if you notice my one of these lines that is represented here, had it been only a natural gas based a combined cycle power plant, let us say it is located in part of India, versus if it is in co-firing or a hybrid mode which involves capturing some solar energy, then what happens to emissions? One has to investigate. You can't say just like that it goes down this way or that way. Then, as we know, solar energy is intermittent. Solar energy is available only typically 10 to 12 hours. So that means when there is a lot of energy, is there a way to store and utilize it in this? So that means what is the role of energy storage? These are not some things that can be discussed in 10-20 minutes in this, or even each topic is in many places like courses, whether undergraduate, even graduate. The whole idea I'm trying to say is some of these topics are like research areas where people are doing. Okay, let me explain two more slides, then we will have the little interaction, please. So this is where you see this is the combined cycle with solar. So this is a traditional gas cycle with all the arrangement. Now you see this is the steam cycle. Now this is what is in a bigger way represented the heat recovery steam generator, or in a way that where steam is produced. Now you see this is the solar field. So this is a typical diagram. Depending on how the solar field is utilized, we can have high concentrated solar system where temperatures can be produced. We can even use to heat the compressed air, or it can be used to produce superheat the steam in the bottom cycle. What I am saying is solar energy is shown here as an idea. Its input could be to the gas cycle or to the steam cycle or combination. And again, that is where lot research, lot publications, they're all going on. Okay, so this is another one. Just to show you, this is a typical. You have a biomass system, you have a solar field, and this is a sort of a hybridized version between solar and biomass. Because what happens if we use only solar? During 12 hours, solar is not available. I'm talking all thermal route, and biomass helps to take care that time. So again, this is hybridized. So the whole idea is if you see here, how the solar is brought in, how it can be utilized in a hybrid mode. This is a hybrid. It's not co-firing. It's hybrid mode. The whole idea being improving efficiency, utilizing renewable, reducing emissions. Again, here the same thing. Okay. So I think before I continue, does anybody has any comment, any question? Maybe I can clarify. If there is any, please. Okay. If not, so I'm going to show you the continuation. Please observe this diagram. Again, you may see a lot of components as you see. So this one here If you remember one of my figure, I may not be able to go back. The first figure I showed you in the energy mix, coal, oil, natural gas still contribute in the globe a lot. And particularly if you see countries like China, US, India, why I told these three countries is, I think now India comes in the order one. Earlier, whenever you speak, you always used to say China is most populated, but I think now India is most populated. So India, China, USA, if you notice, what is the common with them is these three countries are probably, I mean, on the globe, the most energy consuming countries now because of their size, growth, and development. At the same time, the surprising thing, if you notice, these three countries have a lot of fossil fuels, and coal is one of them. Now, a lot of them utilize coals through steam power plant technology. How best the technology may be there is a lot efficiency limitation because it uses modified Rankine cycle. Whereas the combined cycle, the way I showed you, is the most efficient given the way the engines are arranged. So this one here, there are some power plants around the world, please. Lot of research goes on. What you see, this word IGCC, which I'll explain, coal gasification combined, integrated gasification combined cycle. So meaning is the coal, if we use in solid form, has to be utilized only with steam approach, steam cycle approach. Whereas here, you can see this is a gasifier. So what happens is we supply coal, depending on what site of gasifier it is, air-fed, steam, or whatever it is, there is a partial combustion followed by reactions, ultimately producing what you call a syngas. The gas is cleaned. It is cleaned so that no particulates goes into the turbine blades, harming them. Then we have here the typical the gas turbine combustion chambers with a turbine system with a generator. Then you can see whether this unit is there or not, this supplementary unit. Then the waste heat from these turbine system is utilized in the bottoming steam cycle with this steam producing mechanism, these turbines, with the generator, with all other components. So meaning is, if you notice, this coal, which is solid fuel, is converted into a gaseous form, clean. Now we are running a combined cycle. That means gas cycle in the top, bottom steam cycle, bringing down to that combined cycle, which is the efficient form. This is what is IGCC, integrated gasification combined cycle. And this is where I'm telling you, even in India, a lot of research happens, but there are power plants only still a few, because I mean, still there's a lot of research that goes on, and in the future, definitely these are going to come because of their heavy advantages, including high efficiency. Now, the question is, again, for a researcher, for a professor, what is the opportunity? There are a lot of opportunity, please. People do a lot of research. Even I am telling you, with masters or PhDs, even we did a lot, we published. Not only, everybody publishes. When you are in a teaching profession, part of profession involves you have to do research and publish. So what I am saying is there are many areas, from gasification to conducting the performance to systematic. That means the combination of these systems. You can have many varieties of how you propose this integration of the components leading to IGCC form. So supplementary, all these, it goes on. Okay. So I think that's where, again, a lot of opportunity and research purpose. Now this one, just observe in a way. I know there are a lot of components, but let me explain. We have a fuel input, we have a gas cycle system, then there is a heat recovery system, there is a steam cycle system. Then even from the low side, there is a vapor cycle. Meaning here is, as you can see here, the word indicates, it's a triple cycle. Is everything okay? Are you able to hear me? Hello?
Yes, sir.
Okay. So this cycle, if you see, this is a triple cycle arrangement. We have a gas cycle, we have a steam cycle, we have a Kalina cycle. This is a low temperature vapor operated cycle. And the whole thing here it is, now if you look from second law point of view, you have heat engine one where you are feeding heat source. Then the waste heat from heat engine one is utilized to produce some working fluid and run a heat engine two. Then waste heat from the heat engine 2 is utilized to run the heat engine 3, and still there is a heat rejection to satisfy second law of thermodynamics. So meaning is the efficiency of such a cycle is going to be very high. Now, from thermodynamic point of view, we are talking efficiency. There could be cost, other things. So meaning, again, there's a lot of research that needs to be done. That's where a lot of research is going on. And even whatever the thing that is shown here, is conducted by Dr. Srinivas, a professor in NIT Jalandhar, who is a collaborator with me too. So this is one of the work. But the idea here is it's not about whose work. There is so much of opportunity that there is a research, thermodynamic analysis, role of different parameters, role of different things, all these going on. So the whole story, it goes like this. These triple cycles are given from second law point of view. When you derive a general combine their overall efficiency expression goes on. So we need to look into many sides, including economics. Lot of research, lot of efforts are needed on that. So now please observe, I started with a steam cycle. I went on to combined cycle. I went on to co-firing mode of combined cycle. I went on to hybridized version of combined cycles. Then I went on to adding energy storage. Then next I showed you in the last two slides, triple cycle. So see the sequence, all these are based on the second law. Now, next we are at what the heading called multi-generation or integrated energy systems. In my second lecture, when I talk about advanced hydrogen systems, there is a one of the system that I will talk. But here, as you people here, multi-generation means we are trying to produce many things, not only power, process heat, some other things. So the whole idea is the way these multi-generation or integrated energy systems are arranged, they will produce very high performance, high efficiency. So that means what is the benefit that we are going to get? We will have lot reduced emissions, even when we are talking about utilizing natural gas or coal, which are fossil fuels. And not only that, lot of these systems are coming where people are doing research. I tell you, this is a big area now, how to capture carbon dioxide, what to do with that carbon dioxide, and how expensive, what is its economics. So the meaning is the lines that are written here, developments towards integrated systems, performance simulation, emissions investigations with various combinations, carbon capture, each is a question mark. I'm telling you, each is a question mark where we need to do research. You cannot have answers in 1 minute for the systems like this. Otherwise, we could have solved the world energy problems and emission problems, sustainability problems long back. So this is where we have a lot of opportunity. Even in India, you do see a lot of effort that is put, though there is effort towards renewables. Renewables alone is not going to solve quickly everything. It is going to be a long way. So again, there is a long process. So this is where a lot of benefits. Okay. So now I am into my second part of this lecture. As you have seen, I showed you in one part how the systems are getting developed, energy in general, because I have to choose only energy because of the time. Now, in the second part, you are going to see how does this second law benefits when we compare with the first law. Okay, we teach both the laws to students for engineering systems. So please look, as I already said, I'm not here to teach you first law, second law. It's basic meanings. We are all familiar. But how does in research, how does in general in engineering systems, engineering developments, the second law is playing a role? So first law, we know traditional approach, we go with energy balance, do the things, write a code, get the details. Now, if you look second law, why do we worry so much? What does it benefit? So as you recollect, the second law is the one which gives how a process happens in engineering. It gives you direction. And then it brings about quality, please, in a way through irreversibilities. We all know what those irreversibilities are. Then what is the benefit that we are going to get by doing this second law analysis, which is also called exergy analysis? I'll explain what exergy means in few minutes. It tries to tell you many things. Overall, the performance of not only a component, the whole system, from second law point of view, not from first law point of view. First law only talks about energy, it doesn't differentiate a quality, which I will show you in few minutes. So this is where we are going to see whether it is exergy loss, destruction, efficiency, role of different materials, conditions. Now comes then how do we do the second law analysis or exergy analysis? Every thermodynamic book now will provide you the approach. What I am saying is how to conduct exergy analysis or second law analysis. The approach is listed in every thermodynamic book, please, because what we do is I have a system. In few minutes, I'll be going there. Once for a given component, you have the state conditions, then you calculate the availability. Basically, a simple relation. If you see Professor P.K. book or Moran Shapiro, you see this. And here, these zeros represents basically reference. So once any system, let us say you have a gas in a combustion chamber, it can do something till it reaches that of atmosphere, where atmosphere means we represent a reference temperature. So that means there is still some energy available, but it cannot do anything. It's like dead. So basically how much availability is available, the potential from a state high, we can estimate. So this is what is called a typical availability, calculation function. So now the question is, when you know the flow rate, you can calculate the typical, the physical exergy using this. So then what happens? As I said, I'll explain what it means using a system. Depending on the system, there is a physical exergy, chemical exergy. What exergy it stands is, it is like this. Exergy basically gives you the theoretical maximum work that can be produced before a system reaches that of a dead state. So meaning is, if you have somewhere here a system with a potential, it has ability to do something till it reaches that of reference, which is outside or which is a dead state. So that's what we are trying to estimate. Then why do we need to consider chemical? There are also kinetic potential which are negligible. So let me go to a system. Before I go to the system, as I said, in the analysis, most of times we neglect kinetic part of exergy, potential part of exergy. Those are very small components we consider physical and chemical. That is where it is called total exergy input. Now pay attention. I just choose one of the system. So this is a combined cycle, which is a classic example. This is where you see these are compressors. So we give work input, we compress. So if you take here, this is the compressed air at high pressure, high temperature. So with reference to the reference here, it has a physical capability to do something. Now you look in this combustion chamber, please. The moment we feed this here, we are feeding fuel. Let us say it is natural gas. If you look here, the combustion products are different. So with reference to an environment, a reference state, there is alteration which needs to be accounted. So that means there is a chemical exergy. So meaning is, you consider a system like this, go around for each component, depending on, we calculate physical, chemical. As I already said, though there are some velocities, potential, position effects, those two are very small. So then for a given system, what we do is, using this approach, we try to calculate exergy at each location. Then we try to define efficiency. How we define energy efficiency, energy output, energy input? We define exergy efficiency based on the exergy to the exergy input. So then question comes, how does this benefit? Bear with me few minutes. I will take to one slide where we will have even discussion there, and how this second law benefits you are going to see. That's where I want your questions, comments, even input. So now this is just, I put it from one of the student work, a thesis work, to show you the colorful nature of the role of this exergy analysis. And here it is represented in a multi-way. What you mean is, with reference to percentage of exergy input, let us say these are combustion chambers. Then when you have a different pressure ratio, different gas turbine inlet temperatures, so how does the exergy destruction varies in those combustion chambers? Let me just give me 2 minutes. I'll go back to the diagram. I'll explain. So what you see is here, our question here is not about talking these percentage values, the trends. So it shows you the typical variation of the trends with pressure ratio, temperature, the exergy destruction in terms of exergy input. Now let me go back to this diagram. Please observe here. Please observe. We are sending a compressed air here at a typical design pressure with whatever the temperature it comes from here, combustion chamber to, compressor to outlet. Now this is where we are burning fuel. So that means we control, you know what we do? Just pay attention. We are controlling air fuel ratio in this to match to this gas turbine blade material design. Now take for a moment, had the turbine blade is 800 degrees centigrade, 1000 degrees centigrade, 1300 degrees centigrade, you are controlling air fuel ratio. So that means if to match this to 1100 degrees centigrade compared to 800, we fire less air. That means the dilution will be less. If it is 800, we dilute more to bring down the temperature. So meaning is, if you recollect, as I was using the word quality, it is related to irreversibility. The more air we feed into the combustion chamber to control temperature means it's a mixing. There is a quality destruction. So those details are brought out quality point of view by the second law, not by first law. For first law, it doesn't matter which turbine you use it, whether it's a 700 degrees gas turbine blade material, 1100, it doesn't matter. It goes by energy balance. Whereas if it is 1100 performance, you see tremendous improvement. So that comes down to quality here. Again, look here. This is a reheat. So that means these products are going in where we fire less fuel. But question here is the way this quality destruction is different. So how these combustion chambers behave from exergy point of view, second law point of view with conditions can be seen in this figure. Like this, there are many, lot of research are doing research place. Even in India now, you see a good chunk of people, whether they are from different IITs, NITs, colleges, even in private college. See, these days, research is done by researcher, not by institute. What I am saying is, one can be in any institute, one can do top quality research. Yes, sometimes being in a better institute gives opportunity. That's the only advantage, but research goes with the individual and their effort. So now let me go to my classic one. This is where I give you time. Please observe. You see some pattern. Maybe before I explain, if any one of you want to comment on this pattern, I am interested to listen from any participant if it is allowed, if you are able to speak. Otherwise, I'll explain. What do you notice, please? What importance it is giving us? Can I hear from anyone? Okay, I'll go and explain. Please observe. This is percentage of exergy destruction from quality point of view for the same combined cycle. Same combined cycle. Keep this in mind. This is a power plant with so many combinations, so many components. Now, if you notice here, the exergy destruction in different components are listed here. This is from second law point of view. This is from exergy analysis point of view. If I blindly go by first law analysis, then I will be representing performance of compressor, condenser, that combustion chamber, each gives me some number. But by doing through exergy or second law, what I am noticing is, it is telling me the exergy destruction in different components, and it is clearly telling me there are some components. It indicates that the exergy destruction is a lot. So that means there is a need to improve these components if we want to improve the overall system performance from quality point of view, from second law point of view, from exergy point of view. So the whole story is, this cannot be obtained if we simply go by first law. This is where, now tell me, if let us say there is a funding agency or a big industry which is engaged in this combined cycle power generation, they own a lot of power plants, they have technology, they want to modify, improve, further upgrade their technology. They may approach you or me, say that, okay, we'll give you this many crores of rupees. Can you improve even one of this component by some percentage in the next 2-3 years or 5 years? That way, their overall system goes up, their technology goes up, they can sell for high, they can make money. So what I am saying is, this gives us a lot of information, how components are performing from second law point of view. If I have effort and money available, I have a graduate student available, as a researcher, where should I focus my research to improve the system further? I can't go and put in the small, I maybe do, or you may be able to do a little bit of improvement, that is not going to have a big impact. This is where the big impact will happen. So this one, as I'm telling, this one slide alone can be taught for 60 minutes. I'm not doing it. I'm just taking only few minutes. I'm trying to show you what I am saying is any engineering system, irrespective of even it, they may not be related to only thermal or engineering, energy or hydrogen side, but in general, I am telling you, the second law these days is being utilized across engineering disciplines. Though mechanicals and chemicals lead it to help them to understand its law approach methodology, but the story is this gives us an idea the performance from quality point of view, exergy point of view, second law point of view, the room to improve further. Any improvement here has a big impact, and this is what actually led to a lot of blade material development, lot of gas turbines. I told you, if you go to 1970s, 80s, you may be seeing a turbine that operates at 800. These days, I told you, close to 1350, 75. So this is a lot worse. On one side, thermodynamic gave direction to materials development. I know material people say that materials improved the systems, thermal systems or power plant systems or other aircraft systems, whichever way it is, the second law has a role. Okay, so the story is, I think all these leads to what is called, as I was trying to link it to the sustainability side. And I do have some work which will be shown in the next lecture, how to quantify even that sustainability is not just for hydrogen, in general for any engineering system, a methodology that was developed. And this paper I'll be emailing, as I already told, to Professor Kumar. So where you will be getting a couple of journal papers afterwards. So the whole story is we can develop a sustainability method with the details I will explain in the second lecture. So that way we can see, we can compare. So there are platforms developed. People are working a lot. So uh, almost I'm close to my first lecture. Now the question that comes is, as I have shown, taking few power plant configurations, taking one by one, I showed you the role of second law, how second law is helping the design and improvement of them as we understand better meaning of second law. See, second law, first law, these laws were stated in 1850s. See, we are not reinventing them, but the second law meaning and its role, entropy generation, minimization, exergy, I think have received a lot attention only from 80s. And I should state here, I think a lot of the credit for better understanding of entropy and second law concept should be given to a great professor. His name is Adrian Bejan. If you people might have seen a lot of his books. He's a great professor. He works in USA. So the professor has written so many books. I think its initial importance was brought out by that professor, Professor Bejan. Later, everybody works. There are great people. Even Professor Nag has contributed tremendous on this side of it. Now also people are doing. So the whole story is this exergy analysis is leading to a lot of understanding and leads to development in engineering design. Again, performance improvement for all the systems. So we will be working, as I was saying, to improve efficiencies, to bring down the environmental impact, and not one system. I went and talked about multi-generation systems. We are at a stage where in many sites we talk about multi-generation to improve performance. And these are a lot of other things, the conservation other, and leading to sustainability. So now I think I want to acknowledge a lot of I mean, whether organizations or students, and including Professor P.K. Nag, with whom I did long back, though Professor Nag is not anymore. So the whole story is, as I said, the sustainable development, it cannot happen just like that. We as scientists, engineers, professors, researchers, graduate students have a role to play. And it is not an overnight magic, please. If that is the thing, we could have done long back. So a lot slow improvement makes things much better. So that's where we are headed. So from utilizing them, hybridizing them, improving them, understanding them, looking at their combinations, efficiencies, all these things. So I think, are there any comments, any questions? Yes, please. So depending on what you have, I can go over it. Any comments, any questions? Particularly, I am interested to engage you people for a few minutes here. Yeah.
Participants are requested to ask the questions,
Yes.
please.
I want to have questions from them so that that benefits the discussion. I can go to any slide. You just mentioned me the slide. I can go back. Okay.
If any questions, you can ask, please.
Okay, then I'll share one more. If while they are thinking for question, if I have it on my screen immediately, just give me 1 second. See, the way I was showing you this exergy analysis, I know, as I said, typically people teach them lectures, in a classroom or this. So this paper also I'll be emailing Professor Kumar. So you can see it like, I mean, the approach when it is done. This is the system. I try to take it 5 minutes to explain those details. It's not 5 minutes, please. These are done in thesis with months effort. So you start from here, go around with each component, try to develop all the equations. You will get this copy too. So see, first energy analysis is considered. Look here. I know the screen could be small, but still you are able to see. See, we take the fuel, we consider air, then you propose a combustion equation. So as you can see, these are the products. You try to balance to meet to the gas turbine. So that way we get air fuel ratio details. Then we try to make energy balance considering the enthalpies, calorific values. This is what the term that is related to the gas turbine inlet temperature. So that means then we will have. So then we try to, you cannot see if you look here, you cannot get this gas turbine. This is the gas turbine. If this is designed for 1100 degrees centigrade blade material operation, to get 1100, we try to do iteration through a programming. So meaning is, so you set the limits of the gas turbine operation. These two equations are utilized and you develop a code to control that air fuel ratio, to get to the air fuel ratio. Then comes, as I said, so if I go back here, this is the reheat combustor. How do you know? I mean, even if we supply some air, if there is a need, we are firing fuel, a lot of oxygen will be there. So we control this temperature. Again, look here. See, the whole idea me showing is, saying is very easy. When we do work, it's not hard. It takes a lot of time, sometimes 6 to 7, 8 months, 1 year to get a good research work piece and then to publish it. So you can see this is the reheat. Go on, you develop the equations. Then the thing. Now you can see here the exergy what I was showing you. I tried to show you in this presentation because I don't have a luxury of hours to show you all the details. Please see, I just put 2 slides. But now if you see here, you can see every step of the approach is given here, which you are going to get this paper too. Availability, physical exergy, chemical exergy. Then how do we write for each component? See, from compressors to turbine to how the efficiencies are defined. What is the, if you take a turbine, it is producing mechanical work. We are giving some exergy input. So how you define? So for each component, the typical definitions of exergy, efficiencies, exergy destructions, the overall, everything is represented. And I had only opportunity to show you 1 or 2 figures there. But here, like imagine, you observe this one. This is very small on the screen for you. But the question is, if you take this is one parameter, let us say pressure ratio, you're talking about exergy destruction or exergy loss or the parameter, different sets are represented here. If you have a turbines, combustion chambers, heat recovery steam generators, we cannot understand completely without mapping them. We need to generate results through the code. Then you need to map them. You need to see for different combinations how the systems are behaving. They behave differently. So all these details, as I was explaining, were shown. So if we get a better understanding of them, the way I was showing, like here, if you see this particular figure, please, this particular figure, this is a colorful one because I put it there scanned, so it went black. Now you can see here, it tells you. So the whole story I'm telling you is this article, which I'll be emailing again, we give all those details. So the whole point here is, for any system, if we do the second law analysis, it need not be combined cycle power plant. And since there is before I close it, I won't get opportunity to talk the same second law in the other presentation. I just take a little example, please. So don't think the second law or exergy analysis is just for these machines, power plants, in hybrid systems, or some other systems. No, even as a humans, we, how you utilize your time, whether in a day, in a year, or in your lifetime, depends on how much success you achieve. So if you account time, the way we utilize our time, we are bringing irreversibilities. So we can define, even for us, the efficiencies based on first law and second law. I'm telling you, I'll just give very briefly. I won't dwell on too much. If you have 8 hours in a day, you are 10 hours in a day you are working, depending on how you planned, how you utilized, and that makes the difference. Even if you imagine a school kid, this is, I think, one of the classic example in any thermodynamics book. Imagine there's a school kid who comes back to school and has an opportunity of 2 hours of time available. I'm just giving you 2 hours of time available. 1 hour he has to do homework, he or she. 1 hour there's a time to watch or play or the things, whether it's a TV outside. Let's imagine 2 cases quickly. You see this. If you take school kid 1, if the first student watched TV, then tried to go to do the homework, the performance versus the school kid 2, who did work first, assignment or homework first, went on to watch TV or other things, there is a huge performance difference. You know why? The one who watched first TV or something, let us say Spider-Man is falling or going up, when he's trying to, or he or she is trying to focus on the work, that comes in the mind and disturbs the mind. So versus the second one, who completed the work first, then went on to watch, enjoying the 1 hour leisure time or play time, whichever way you name it. So that means in any analysis, when you apply the first law and second law, the quality mode, the performance is going to be different. So those details can be brought out utilizing the second law or exergy rule, not for these power plants, not for IC engines, not for turbines, not for lathe machines, for any system, including for us as humans, as I am telling you, which will benefit our performance too. That's why sometimes you see the great people, sometimes we say are the successful, means they know how to utilize the time, how to plan even, because everything is part of irreversibility. I think still I just want to give some time. If you have any questions or interactions, at least I want to hear. If not, I'll go to my second part of the lecture, please. Any comments, any questions? Okay.